Hello everyone, welcome back. Let me introduce our next speaker, Dr. Paramita Ghosh. So Dr. Paramita Ghosh holds the position of Senior Project Engineer at CRAC. Currently, she is deeply engaged in MSCC application support activity, a pivotal initiative under the National Supercomputing Mission. With a wealth of expertise in high-performance computing, parallel programming, and the development of numerical methods and programs, Dr. Ghosh brings invaluable contribution to her team. She is deeply involved in the development of a massively parallel density functional theory program, which is known as AMDKIIT. We'll just wait for 5 more minutes and then we will start the session.
Thank you, ma'am, for introducing me. Hello, everybody. My name is Paramita Ghosh. I am a senior project engineer at CIDE, Pune. This is the outline of my talk. First, I will give introduction of AMDKIIT.
Paramita, slides are not moving.
Stop sharing. Okay, now it is visible.
Yes.
Okay, so this is the outline of my talk. First, I will introduce the software AMDKIIT. Then I will describe the key features of the software. After that, I will focus on the input file, the format of the input file, the keyword, all I will describe in details. After that, I will describe some task specific input so that user can set their own parameter and run run DFT calculation using this AMDKIT software. After that, I will explain the output file and I will explain various part of the output file. AMDKIT is fully developed within the academia of our country. The source of AMDKIT is open and freely available to all under MIT license. In order to run AMDKIT, we need 4 libraries: LAPACK, FFTW, libxc, and YML. We need CMake-based compilation, either GNU or Intel, and API. So, Shubhajit will cover this part in details later. Now, the main features of AMDKIT. As of now, AMDKIT can perform wave function optimization. both for open cell and closed cell calculation. It can perform geometry optimization and Born-Oppenheimer molecular dynamics. Our source code is available in GitHub. If user want, they can download their own code. Okay. So next is input file. There are three types of input file required. One is coordinate file, another is pseudopotential file, and third one is the main input file, which is required to set the parameter of the system. So first, focus on coordinate file. Coordinate file, the geometry of the system has to be provided in the form of XYZ. User can build their structure using any software like Gauss View, Avogadro, VMD, Molden, etc. So suppose let's take an example of water molecule. So this is the format of XYZ file. First line represent the number of atom in a molecule, total number of atoms in a molecule. So for water, this number is 3. Then the second line basically comment line. Here it is represented as species name H2O. After that, first column represent atom level and second, third and fourth column represent X, Y and Z coordinate. Next is pseudopotential file. AMDKIIT software is plain wave based electronic structure theory code with pseudopotential. To use plain wave, user need to provide the correct pseudopotential for different atoms. Currently, non-conserving pseudopotential are enabled. It has to be built for the XC correlation which is being used during the calculation. Both PSP format and UPF format can be used. So using this link, user can download the pseudopotential file. So I will show you how to choose that. So in this case, you can see that there is some warning. They are only available for PB functional. Use 4.1 for LD. Suppose we want to use LDA, so I have to change here version, then select after that format UPF. Then if you simply click on the atom, then you will get the pseudopotential file. So in this way, user can directly download the pseudopotential file. Okay. Now next is our main input file. So input file is in YML format. User can choose their own file name, but format should be in YML. Every keyword will be in uppercase. For each keyword, there will be always a gap after colon. You can see here I have given one sample input YML file. So after each keyword, there is a colon. After that, there is a gap. So this gap is required. And another point is that for a new sub-dictionary, there will be at least one gap in the next line to start new sub-dictionary. That means you can see here in the optimization, there is new sub in the next line, there is new sub-dictionary wave function. So before wave function, there is a gap. Okay. Now, next, I will discuss each keyword in details. So first, task. As of now, I have said already that AMDKIIT can perform only wave function optimization, geometry optimization, and molecular dynamics. So user has to choose this task name as in this way, like wave function underscore optimization to perform the single point energy. Okay. Now coming to the next is the optimization part. So here we are doing wave function optimization. So here we are given optimization wave function, then minimizer. These basically specify the algorithm that will be used to optimize the wave function of the system. Next steps, this is the maximum steps for the wave function optimization, and third one is the gradient cutoff. This parameter specifies maximum allowable value for largest element in the gradient. This part is optional. That means if you want to use this part, you can use, or you can skip this part. If you skip this part, the code will by default take this value minimizer as conjugate gradient, maximum step as 800, and gradient cutoff as 10 to the power minus 7. But if user want to choose suppose 100 step, they can use this keyword and simply mention here 100 like that. Okay. Now next is the symmetry. So symmetry of the supercell has to be defined here. So you can use any symmetry. So here I am using cubic, so I have mentioned it cubic. Next part, this gives the information regarding the supercell. So first unit, this unit specify the dimension of the supercell in angstrom unit. This is the dimension. This basically represent A, B, and C. And next is the angle alpha, beta, and gamma. After that, input part. This part I have already discussed. So whatever coordinate file you are using, you have to give your file name. Here I am using input underscore coordinate dot xyz. That's why I am giving here this name. And this is the unit in which unit you have used inside this file. I mean, in which unit you express your coordinate. So that unit you have to mention here. After that, label. This label is to specify the atom. So I have already shown that in our test case we are using water. So for water you can see here. So first column oxygen. So this is basically the labeling. So you can see here level 1 atom oxygen, and pp file represent the pseudopotential file required for that O atom, that means oxygen atom. Then the pp scheme, this scheme basically required to calculate the non-local part of the pseudopotential. If user want to use this claim and Bylander scheme, they can use it. If they don't want to use it, they can simply mention here none. Okay. Lmax, this provides the maximum value of L, which is used to calculate the pseudopotential part. So in this way, if we have more than one atom, then we have to specify level for each type of atom. So here we have two types of atom, oxygen and hydrogen. So here we are expressing like level 1 and level 2. Now next part is DFT. So DFT part, this part basically define exchange correlation functional to be used in the calculation. Here you have to be careful that sorry, in pp file I am using uh, oxygen underscore empty underscore LDA dot PSP. That means in pseudopotential file we are using LDA exchange correlation. So in DFT part also I am using LDA. So user have to be careful here. And these functional are available in this link, and user can check this file inside the libxc library for details. Now, if we summarize the whole thing, so first task name, then symmetry, then the cell information. After that, you have to give the coordinate file information. After that, atom information, and last, you have to give exchange correlation functional. So these all are mandatory field. You have to mention this field before running the calculation. Okay. So now after running the calculation for wave function optimization, we will get two types of file. One is AMDKIIT.out. This file contains all the details of the calculation like input details, system details, optimization details, all the information will will print it here. Will print here and sp underscore energy dot dat. In this file, consume energy versus step will be printed. Okay, so after that optimization, you can simply plot energy versus step. You can get how energy converge with step. Now, if anyone want to perform geometry optimization, simply you need to change the task. Other part code will automatically take care. But if user want to specify their own like minimize the type, maximum step, gradient cutoff, they can use it, but this is optional. So after performing geometry optimization, we will get three types of file: amdkit.out, similar as earlier, and then atom underscore quad.xyz. This file basically print the coordinate during the geometry optimization. User can visualize the structure during the geometry optimization using this file, and atom underscore force.dat will contain force information during the geometry optimization. Now, next is molecular dynamics. So in order to perform molecular dynamics, you can specify three more variables here. First, temperature, then maximum step and time step. Temperature is 300 Kelvin. Here unit used in Kelvin. Maximum step by default use 999 and time step is 1 femtosecond. Please keep in mind time step is in femtosecond unit. Now, after running the molecular dynamics calculation, you will get three types of output. AMDKIIT.out. Along with that, you will get MD underscore energy dot dat. This will contain the energy formation. In each MD step, it will print consume energy, total energy in every MD step. Okay. And similarly, MD underscore trajectory dot xyz will contain the coordinate or the geometry of the system at every MD step. So if user want to visualize their system, they can visualize using this trajectory file. Now, how the output file looks like. So, this is the output of AMDKIIT. Here you can see that first version, then you will get the information of date, time, then it will print number of processor used to run this calculation. After that, all the input details used to run this calculation will be printed here. So, okay. So this part basically gives the input details. Now, the next part, it will print the simulation parameter. Here we can see that wave function cutoff used here 1880 Rydberg, density cutoff 320 Rydberg, and exchange correlation functional is xc underscore ld xc. Then it contains supercell information, after that species information, and after that it will print the division of X, Y, and Z grid along the processor. So we are using 48 processors. So here you can see that the division along these 48 processors, division of X, Y, and Z grid, and also the grid in G space. So up to this 48. Then it will print total number of valence electron, occupation number. Then it will give the optimization details. So wave function optimization, the details is printed. Now it's giving consume energy in each step, energy change, then maximum gradient, and last column represent the CPU time at every step. So see, at last we can see that total energy of the optimized system. Okay, so this is the output of AMDKIIT. Now, my colleague Subhajit will show how to install and compile the AMDKIIT.
Before we start, I'll just tell the overview of the system which we are going to use for our hands-on session. For the hands-on session, we are going to use Param Brahma HPC system. Param Brahma HPC system is having peak computing power of 1.75 petaflops, and the system is deployed under NSM and it is located at IISER Puri. The system is having total 179 compute nodes, out of which 140 nodes are CPU nodes and the 39 nodes are high memory nodes. And this CPU-based 140 nodes are further divided in CPU-based and the GPU-based nodes. The CPU nodes are 108 and the rest of the 32 nodes are having NVIDIA V100 GPUs connected to each node. Those are the GPU-based nodes. The total memory of the system is 56.8 terabytes. And the storage on the system is available. It's a luster-based primary storage. It's 750 terabytes of this storage. Each of these 179 nodes are connected with 100 Gbps of Mellanox InfiniBand interconnect, and the secondary interconnect is 10 GB or 1 GB Ethernet network. So I'll further tell you about this 179 compute nodes. These are the three categories. CPU only nodes are 108 nodes, which is having, each node is having 192 gigabytes of memory, and each is having two socket. Each socket is having 24 cores, and it runs across 2.9 gigahertz of frequency. The high memory nodes, each node is having 768 gigabytes of main memory, and each system is having dual socket, and each socket is having 24 cores. The rest of these 32 GPU based nodes, these are the same like a CPU node, with the 192 gigabytes of memory, and these are also these are like Intel Skylake based processor, and where each node is having dual socket, but each socket is having 20 cores. So give me some more. I'll just take a few more minutes of your time, and I will just talk about this the web page again. So once you log in onto this web page, the summary page has some links here. So it will show if you want to have the more information about this software, you can use this link. This will provide you the more information on each of these software. And if you would like to download and install the software, the link is given where you can download the software and install on your own system. If you want to use the test input data, so the test input data is also provided here. You can download and use run this software using this test sample. And we are already put at this link where we are going to upload our training videos. So this will be the videos will be available after a week time. So if you have any issues, we have this support system available. You can put up your queries on the discussion forum. So the developers are also joined this forum. So the system side support and from the support from the development team also be available onto this forum. So we encourage you to put up your queries and any information related to materials and computational chemistry. If you would like to know, you join this forum and put up your queries here. And other ways to get the help are you can raise the tickets. So you can raise a ticket from this link only. This is the ticketing. You can raise the ticket. Or the other way is you can drop an email to the AMDKIIT mailing list. So we request you to join the AMDKIIT mailing list. This is not only for the AMDKIIT, but you are joining the community of materials and computational chemistry software applications. So this will be helpful if you want some information in this area, or if you want to contribute in the further development of any of these software, because all these software are open source softwares. If you would like to contribute, if you need any guidance in the materials and computational chemistry applications areas. So because the PIs and the developers and the application support team all are the part of this mailing list and discussion forum. So we request you and encourage you to be a part of this community to help each other and grow together. So download link is also available on this page. You can download the AMDKIIT and the other software. Thank you. I'll just introduce our next speaker, Shubhojit Das. Shubhojit Das is a project engineer at CDAC. He is working for the project Material Science and Computational Chemistry under National Supercomputing Mission. He holds a postgraduate diploma in high performance computing application programming from CDAC Pune and has done his graduation from West Bengal University of Technology in the area of information technology. He is actively involved in parallelization and optimization of scientific application on multi-core systems and HPC system like Param series of supercomputers. So thank you, Shubhojit. You can take over and start with the session.
So this is the hands-on session on AMDKIIT application that we have discussed as of now. So I will be carrying on this hands-on session from here. I am Subhojit Das. I am working as a project engineer in CDAC Pune. Yes, sure, ma'am. Moving on to the outline of today's session, what I will be discussing today is I will be covering the installation and compilation of the software. If anyone wants to install this software on their own system, Linux-based system, So what are the requirements they need to fulfill to install software in their own system? I will be covering those part uh, making it available in your own system. So after that, I will be showing you a test calculation by running it on Param Brahma system. I hope everybody will follow the step and run it on your own account that we have provided you with. Or if you have your own account previously, then you can use it and run our input files. Lastly, I will be carrying on a hands-on session in which we will be providing couple of exercises that you can perform and provide us with the feedback that how your output file came, and you can share the screenshot in our discussion forum also. Moving on to the prerequisites in the system that we will be needing if we are installing the software. So there are a couple of prerequisites that we will be required during the installation. Is we will be needing a Unix environment and a CMake software for the cross compilation of the software. So inside this Unix environment, what we will be required is Fortran compiler. Namely, it can be GNU or Intel. Our application supports the compilation with both the compilers. So feel free to use any of the compilers while the installation of the software. And for moving further, we will be needing MPI libraries for the parallel installation of the software. So make sure the environment is enabled in the system. So these are the couple of environment that will be required during the installation. Moving further, what are the application specific requirement that we will be needing while the installation of the software? So firstly, you can see the link that we have provided you with. So you can download the entire software from this GitHub link, or you can just clone this software into your directory. So here we are providing you with a command that is unzip the file. So if you are downloading it in a zip file, you can just copy this command and unzip your file, which will make a directory called AMDKIIT.main. So you will find this directory inside the directory you will find the hierarchy of the directories. Inside the uh, main focus will be on our source directory. So this inside this source directory, we will be making the changes for the installation of the software. So the major changes that we will be needing during the installation of our software is you will be needing to download this YML-CPP file. We have provided the link in the manual that we have provided in the GitHub link. Also, you can see in the slide, we will be sharing this slide to you as well. So you can just git clone this directory into the source directory, and you are well enough to go to the next step. So inside, moving on to the further step, the requirements are you will be needing these three libraries that we have mentioned, namely FFTW, BLAS, and LEPAC, and libxc. So the reference to this libraries are mentioned in this slide, and we have provided this in the manual also. You can uh, click over this link and just go to the website and download. These are the official websites. You can just download the libraries from there. And these libraries require standard installation that are provided in the README file of this uh, libraries. Whenever you're installing, make sure you are installing with the process they have provided with. So we are not covering this installation of the libraries as of now, but if requirements is needed, we will be providing a separate session for the installation of the libraries also. So now if you are installed it in your system, the next changes that you need to make sure in the source directory is you have to find a file, namely cmake list.txt. Inside this file you will be finding three sections: set math root, set fft w root, and set libxc root. These three sections are needed to specify the path where you are installing the libraries. So whichever directory you are installing the libraries, you need to provide the path with, say, here the set math root path is required for the ff for the BLAS and LAPACK path, and set FFTW root will be required for FFTW the installation path and libxc root respectively. You can just provide the path and you are good to go to the next step. So before moving to the next step, what we need to cross check is our MPI environment is uh, enabled entire the session. Whatever installation we are doing, the version should always be the same. And we can move on to the further uh, compilation. So during the compilation of the software, uh, here also we need to check, this is the final compilation of the software. So here we need to check the version of the MPI environment that we are using. So after checking it, making sure that the libraries and this version matches, and next we will be checking the GCC version of the software. This should also match. Sometimes the version mismatch because the by default GCC is taken by the system, and the GCC we are using might change. So we just need to cross check before every installation. So moving on to the further step that we will be needing is to make a build directory in the source file, source directory. So once we have made this build directory, you can just run this couple of commands, cmake dot dot. This will configure the directory, and after this you can just uh, co copy this command, make command, and this will just make a executable file, namely amdkit.x. This is the final output executable file that you will be needing for to run the test cases uh, while you are running different calculation for our AMDKIIT application. So the next slide is talking. In the next slide, I will be talking about the input required to run the test calculation. Here are mainly we have discussed previously, but in the for the hands-on section, I need to discuss it briefly. That this three files we will be needing in our directory from where we are running the test cases. So pseudo potential files, whichever molecule we are running, their pseudo potential files should be present in the directory. The input.yml file, this is the main input file, as discussed previously. This is the main input file where which calculation we are trying to run should be specified here. And the input underscore coordinate dot xyz is the input coordinates for the molecule that we are providing. So these are the main three input files that must be present inside the directory while running the test cases. Make sure these are present before submitting the job. So moving on to the next uh, part of our session is, what we have done is we have installed this entire AMDKIIT software inside Param Brahma, on the Param Brahma cluster, and we are providing you with a module file to set up the environment to run the test cases. So you can just type a command module level, and you can check this module available on the Param Brahma system. I encourage Param Brahma users to just once check this module is if available on their system. So I hope you can see this module loaded in your module in the Param Brahma cluster. You will be just needing to just load it, and you are well enough to run your test cases. I will be showing on the further session. So moving on to the next slide, that we need that we have provided you with the test case download link in the chat section, and also we have mailed it to you on your registered mail account. So if I insist every user to just copy this command uh, uh, and just try it cloning into your directory. This will make a directory inside your wherever you are cloning. This will just make a directory name mscc-test input. I will be waiting for a couple of minutes, and please confirm if you are having any error.
If anyone have any issue till now, any query, they can ask.
Simply raise your hand if they are not.
Feel free to raise the hand section that we have that in the uh, section above provided. You can raise your hand and let us know if you are having any problem. And discussing further about this module or the application that we are providing to you, this AMDKIIT application we have installed successfully on Param Brahma cluster. You can use it full-fledgedly however you are wanting. If you are wanting to use with your own test input files, you can also try using it and explore our software to the extent uh, uh, of the computational power of Param Brahma. So feel free to use and let us know in our discussions forum, and we will get back to you if any problem occurs. So this is the download link. I hope everyone can download the link. We have provided the git clone link in the chat section. If you are having any problem in seeing this command, you can just clone it. You can just copy it.
I'm requesting all of you, please try this. If you have any issue, please let us know.
I hope you all are you all have successfully downloaded the test inputs, so we can move further. Executable first, then next is with a space we will be providing the input.yml file, which provide the specification about the computation what we are doing, and finally with a greater than sign we will be writing the name in which we will getting the output of our serial command. So this is the general typically this is general output format for the uh, test cases. In parallel, what we will be doing is just adding this mpi run command and the number of cores that we will be needing to compute the um, test input test calculation. Further we will be providing that amdkit.x executable file, and with the space we will be providing that input.yml file, and the name as per your need you can write modify this name and you will be getting the output. This is the these are the couple of commands to run the test input.